This is a review of the Year 9 end of Term 4 test for 2020. I propose to take you through and do the test as we go so that you see my thinking, you see what the right answers are supposed to be, and I can give you some tips in terms of the examiner's perspective. So, question 1, speed and velocity are different quantities. Complete the sentence. Velocity is a vector. You need to just know that. And velocity is speed in a given direction. 1 mark for each of those. Figure 1 shows the distance time graph, so you're thinking about how to interpret distance time graphs when you read that. Distance time graph for an athlete in a running race. Use figure 1 to determine the distance of the race. Well, if we look up here, the race stops at E, and that is 2 small squares above 40. Each small square is 1, so it is 42 kilometers. Nice and easy. The time taken for the athlete to complete the race, well, that is, we are 2 small squares across there, and each of those squares, what have we got, is worth 10 minutes because 10 squares is worth 50 minutes. So each of those is 5 minutes, 10 minutes then for the 2 squares, 210 minutes. What is the motion of the athlete between B and C? Well, you have a straight line, so it is a constant speed. So there's the answer there. Moving at a constant speed. Which section on figure 1 shows the athlete moving at the highest speed? So here we're looking for the steepest part of the graph. And the steepest part of the graph, to me, the one with the biggest gradient, because of course the gradient of the distance time graph is the velocity or the speed, it's A to B. So that's the one there then. How does the section you gave as answer in part D show the highest speed? Well, it has the highest gradient. It is the gradient we're after there. Or it has the highest or largest gradient. Either of those 2 answers or 3 answers would do there. The car following the race accelerates at a constant rate in a straight line. The velocity of the car increases from 1.9 meters per second to 3.4 meters per second in 60 seconds. What's the change in velocity? Well, the change in velocity, of course, would be 3.4 minus 1.9, which is 1.5. Calculate the acceleration of the car. Well, the acceleration is the change in velocity divided by the time. So it is 1.5 divided by 60, which is 0.025. So there we have 2 of our marks, and our final mark then is for the units, meters per second squared. So in an exam, I wouldn't expect the question to be split like this. I would expect it to say, this is the situation, what is the acceleration, and for you to get 3 marks for that, including the unit. So you would be expected to know the formula, and if you don't know the formula, you will get no marks for the calculation. If you write down the wrong formula, and you even get the right answer, you're still going to get nothing. You cannot get any credit for using the wrong formula. And note the meters per second squared for the unit. Which graph shows how the velocity of the car changes as the car accelerates? Well, if we go back to the question, it says accelerates at a constant rate. So you have a constant acceleration. The gradient of a velocity time graph is the acceleration. And so you're looking for a straight line of constant gradient, constant positive gradient. It's that one. That has no acceleration. That has an acceleration followed by a deceleration or a negative acceleration. And that has a constant negative acceleration. It is B is the answer there. Question 2. We have a slinky representing a sound wave. We have the coils of the slinky. The hand will move backwards and forwards there to make these different patterns. So A, if you followed the note on Classroom, A down here, rarefaction. I will accept low pressure area. B is a compression, and again I will accept a high pressure area. And C, the distance between the middle of one compression and the middle of the next, well, that you should know is the wavelength. So there it is, 3 marks. You just need to be able to label those diagrams like you were told in class. Information from a hairdryer. Which of these is the power? Well, of course, power is measured in watts. It's got to be 2,100 watts. What is the equation which links current, potential difference, and power? You need to know this equation. You need to remember it. So power is potential difference times current for 1 mark. Now remember, in your GCSE, your physics GCSE, about 40% of the marks will come from maths and the application of it. If you don't know or you're unable to use the equations that you need to know, you are going to drop those 40 marks pretty much, or 40% rather. That's disastrous. Make sure that you know your equations. Part C, mains electricity. What is the frequency? It is 50 Hertz. Again, you need to know that. So make sure that you do. In this case, there's only 1 mark, so the capital H small z is not required for the mark, but you should know the units. You should know how to write them down. It is either capital H small z or it is the word in lowercase. You can't mix that. You can't have a capital H there. You can't have a lowercase h there. Neither of them is acceptable. Some electrical appliances use batteries. What type of current does this battery supply? Only direct current from a battery. The hairdryer is connected to the mains electricity supply by a plug. Draw a line from each wire. Live is brown, neutral is blue. The insulation around the earth wire has 2 colours, green and yellow in either order. Green and yellow, yellow and green. Brass is an alloy of copper and zinc. Give 2 properties of brass that make it suitable for use in a plug. Well, clearly it has to be an electrical conductor, it would be pointless to use something which was an insulator. So what else makes it good, do you think? Well, I think if you consider what happens with plugs, they're in and out of the wall quite a lot. You want it to be a hard material. That's pretty much all I would think of. But if you think about other metals that you could use, sodium's a metal. Sodium isn't hard, but it is a conductor. It's also very reactive. So you wouldn't choose to make the prongs of your plug out of sodium because it would corrode really, really quickly in air. You wouldn't make them out of aluminium because they're soft. Aluminium's very easily bent. So corrosion resistance, hardness, and electrical conduction would be three things you could say. I would have gone with conduction and a hard material so that it doesn't bend or wear away. Part H then, describe how power is transferred from the power station to the consumers. So you have a step-up transformer, you have overhead cables, you have a step-down transformer. And this is a 4-mark question. So we're looking to make some good points about this. What are we going to say? We step up the voltage, or better, the potential difference, which decreases the current, since power equals potential difference times current. This reduces the heating of the cables, and so increases the efficiency of the transfer of energy. So I'm quite happy with that. Transformers and cables are the national grid. We step the PD, potential difference, down again at the consumer end of the grid. And that's because high potential difference is likely to cause arcing. That is to say, if you've got 132,000 volts from the cable and the earth, you put a tall building in here, or a crane or something, it closes the gap between the cables and earth, and that very high voltage could jump, a spark could jump from the cable through the crane or through the building to earth. That's dangerous. So out in the countryside where there aren't any tall buildings and cranes are not likely to come underneath the cables routinely, then it's safe enough. But in here near the towns, or in the towns and cities, near homes, near high-rise blocks, all that sort of thing, you step it down so that there's less likelihood of that arcing taking place. And we don't use it at 132,000 volts. We use it at maybe 3,000 volts for heavy industry, but typically 415 or 230 volts in schools and in homes. So that's what I would say. The mark scheme talks about the cables transmitting at very high potential difference, the transformers changing the potential difference, the cables being at a higher potential difference, the step down decreasing the potential difference, step up increasing the potential difference. The potential difference for the consumers is lower than at the power station and lower than in the cables. So I'm happy that I have covered everything in the mark scheme there. But what I did, without looking at the mark scheme, I said, well, I've got the step-up transformer, step-down transformer, the cables. My examiner might want me to know that this is the national grid, so I'll say that. I'll say what a step-up transformer does. Steps up increases the voltage. Why we do that? We decrease the current. Why that's a good thing, reduces the heating in the cables, so it increases the efficiency. I meant to say what efficiency is. So there it is. There's your answer to that question. Question 4 then. An athlete takes part in a race. What's the main force that opposes the athlete's motion? Well, that's air resistance. You might say drag. Wind resistance isn't quite enough. Air resistance is what we're after. Because even if there isn't any wind, there's still going to be air resistance. Which section of the graph represents a part of the race where the resultant force on the athlete is 0? Well, you're looking for a section where there is no acceleration, because if the resultant force is 0, by Newton's second law, F equals ma, there will be no acceleration. And that, of course, is between B and C. Second athlete starts the race at the same time as the first. The second athlete moves with a constant acceleration of 1.6 meters per second squared for the first 6 seconds of the race. The first athlete travels further than the second during the first 6 seconds. Determine the extra distance traveled by the first athlete over the first 6 seconds. So our first athlete travels 6 seconds. They travel the area under the graph then. So you've got .8 times 12.2 and we have the rest of it then. we have 2.2 is the rest of the time times 12.2. So that's the area of the triangle. Sorry, that should be half of that. So the area of the triangle in there, half base times height, half of 3.8 times 12.2. And then we have the area of the rectangle, which is the rest of the 6, 3.8 away from 6 gives you 2.2 times 12.2. So that's the distance traveled by A. And the second athlete moves with a constant acceleration of 1.6 meters per second for the first 6 seconds. So your second athlete is going to end up at 1.6 times 6 meters per second. That's going to be the velocity, the final velocity. So this point, we're working out the value of that. Times 6, so that's the velocity, the point up here. It's going to be a triangle. So the area of the triangle, if we think about the second athlete, they're going to go from 0 to 9.6. 6 times 1.6 is 9.6. They're going to be up here, 9.6. Uh, 9, 2, 4, 6, 9.6. They're going to be here at 6 seconds. So 9.6 times 6 divided by 2, that gives us the area of that triangle. So 9.6 divided by 2 times 6, 28.8. This one, we've got 3.8 times 12.2, and half of that, 23.18. Gives us 50.02 meters. The difference then is 21.2 meters. Question 5. Human catapult. Person lies in a cradle which is held to the ground. The cradle is released. The person is launched vertically into the air by an elastic rope. The person then parachutes back to the ground. Not for the faint-hearted. In position A, there is a store of elastic energy. In position C, the person is at their maximum height. Describe the energy transfers from A through B to C. So I think we're probably assuming that they're about to leave the catapult at this point. So we have elastic potential energy. Let me just get my cursor to work. So we have elastic potential transfers to kinetic. Now we want to be sure that our examiner knows that we have a fixed amount of energy here. Energy is conserved. Now, what else might happen? Well, some energy is going to go into air resistance, or by virtue of air resistance. So we're going to have you could also say that some energy is lost as internal energy of the elastic. You know, if you take an elastic band and you stretch it and release it over and over again really quickly, the elastic band gets a bit warmer. So you've increased the energy stored in the elastic band, in the material of it, and you've increased the internal energy of the elastic. So you could say that too. Not only are we increasing kinetic energy, but we're also increasing gravitational potential. So as the elastic contracts here, as it's getting shorter, he's moving up and he's moving faster. There comes a point, of course, when he leaves the elastic. He's no longer with the elastic. And so once he leaves the elastic behind, we have kinetic energy being transferred to gravitational potential energy, and I'm going to stick GPE there as my abbreviation. Should never use an abbreviation without saying what it is. So, the Marsh scheme says the elastic store decreases, KE and gravitational stores increase between B and C, that's between A and B. Between B and C, the KE decreases, the GPE increases. And what I haven't done is to say AB, and there's BC. Okay. When stretched in position A, the elastic rope stores 25,000 joules. Notice joules in lowercase. Needs to be a capital J on its own or the lowercase word. The elastic rope behaves like a spring with a spring constant of 125 newtons per meter. Calculate the extension for 4 marks using the physics equation sheet. So you're going to say the energy stored is a half K E squared or X squared. I don't happen to remember which form it's in on the equation sheet, but it's a half times the spring constant times the extension squared. So We know we've got 25,000 joules, and that is a half times the spring constant, which is 125, times the extension squared. So then our extension squared is 25,000 times 2 to get rid of the half, and we divide that by 125 to get rid of that. So rearranging the equation, 25,000 times 2 is 2 times a half times 125. 25,000 times 2 divided by 125 gives us just e squared on this side, and the answer then is 20, because you then take the square root of all of that, 50,000 over 125, which gives you 20.